Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Hey everyone, Sam again with another quick TWIMLCon update. One of the things that's been especially exciting to see is the number of organizations sending multiple people, in some cases entire teams, to TWIMLCon to learn about scaling and operationalizing machine learning. A full third of the companies attending are sending groups, in many cases 3, 4, and 5 people. This is awesome. Seeing so many teams attending is a great indicator that folks really see the opportunity associated with improving the efficiency of their data science and machine learning operations, and are excited about the conversations we'll be curating at the event. If you'd like to attend TWIMLCon with your team, just reach out to me at sam@twimlai.com and let's make it happen. Of course, you're welcome to reach out to me if you want to attend as an individual, or just head over to twimlcon.com/register to sign up. A hearty thanks to our friends at Qualcomm for sponsoring today's show. As you hear in my conversation with Tijmen, Qualcomm has been actively involved in AI research for well over a decade, leading to advances in power-efficient, on-device AI through efficient neural network quantization and compression, and more. Of course, Qualcomm powers some of the latest and greatest Android devices with their Snapdragon chipset family. From this strong foundation in the mobile chipset space, Qualcomm now has the goal of scaling AI across devices and making it ubiquitous. To learn more about what Qualcomm is up to, including their AI research platforms and developer tools, visit twimlai.com/Qualcomm. All right, everyone, I am on the line with Tijmen Blankevoort. Tijmen is a staff engineer at Qualcomm, leading the compression and quantization research team. Tijmen, welcome to This Week in Machine Learning and AI.
Hey, it's great to be here. Nice to meet you all.
Great to have you on the show. I'm looking forward to our conversation and digging into the topic of quantization and compression. But before we do that, I'd love to hear a little bit about your background.
Yeah, so I have a background, a bachelor's degree in mathematics from Leiden University. And then I moved to artificial intelligence in Amsterdam. And during my master's, I started my own company together with Professor Max Welling, who's been on the show before, I think. And that was quite successful. So our AI startup got acquired by Qualcomm. And now I'm here already since 2 years now, working in Qualcomm.
Awesome. And what was your role with Scyfer?
So at Scyfer, basically co-founder. Officially, it was called CTO.
Okay.
So I did a lot of the technical stuff, leading the technical team. But I also did a lot of going to different companies, talking to them about their problems that we could potentially solve with deep learning, being on stage a lot, doing some sales. I mean, if you have a small startup, you have to do everything, right? So I did everything.
Wear a lot of hats. Absolutely.
Yes, exactly.
And so at Qualcomm now, your focus, has it been on quantization and compression research the entire time, or have you done a variety of things in a couple of years?
Yeah, that's been it for me. And so basically 2 years ago when I joined, I found this topic of neural network compression and quantization incredibly interesting. So I started working on that, both on the research end and in the application end. And then as I went, the team was growing and the topic became more and more important. Basically the last 2 years of my life have been making neural networks more efficient.
Awesome. And so quantization and compression, what are defined for us this topic, and are they the same thing? Are they different things? How do they, what do those terms mean? Let's start from the top.
Yeah, that's good. So in general, what we're talking about is deep learning in an efficient way, right? So instead of having these very big, large neural networks that can't be run on, for example, a cell phone, we want to make them as small as possible, that they're very efficient and very, very power efficient, that they are quick and fast, etc. So there's a couple of ways that you can do this, right? You can take a network and make the architecture more efficient, for example. Or you can optimize the kernels that execute. Or you can develop specific hardware for making neural networks more efficient. And specifically what we're looking into is, also, of course, those topics. Right? Qualcomm is looking into all of those things. And specifically, my team is looking at compression and quantization. Compression being, let's say you take any pre-trained network. So a network that somebody trained for a task. You spend a lot of time on this, right? And then comes the question, like, how can we run this more efficiently? And with that question, you want to make sure that that same network that you have and that you've trained and put a lot of sweat in, and that you make that one as small as possible. So the idea with compression is remove individual weights, or perhaps even better, remove complete feature maps, complete neurons, complete convolutional channels from your network to make it more efficient, right? And parallel to that, another way of making your network more efficient is quantization. Normally, when you train a neural network, it's done in like floating point 32. So that means that every number is like a 32-bit value. Now you can calculate a lot more effectively and efficiently, and you have a lot less memory transfer and energy consumption if you would use less bits for each of the weights and the activations in your neural network. So the idea is that you can do your calculations in 8 bits, quantize your whole network, both the weights and all the operations in between to 8-bit operations, and then you're a lot more efficient. So both work together, compression and quantization, to kind of scale models down. And sometimes you can do this with like a factor 80, that your model becomes a lot smaller than the original model that you started with.
And how dependent on that compression factor is the specific model that you're working with?
So like you mean how much you can compress it?
Yeah, absolutely. Yeah.
Yeah. It's very important what model you start with. Like, I think there's this running joke in the compression literature that everybody always tests their models on like VGG, because the VGG architecture is so inefficient that you always get these huge numbers, like, oh, I compress my models by a factor 20 or something like that. So those models can be really, really efficiently compressed. More recently, the smaller models are not as, you can't get those big compression numbers. But very frequently, we've seen, for example, MobileNet V2, which is already a very efficient, fast network, can still be compressed by factor 2 sometimes. And that's like a factor 2 less energy that you're using, right? Or a speed up in terms of your latency. So that's quite significant.
And so a lot of the networks that I've heard you toss out are CNNs. Is that the primary place that we're focused on quantization and compression, or does it really span the gamut in terms of the types of models?
Yeah, I think like any model that you want to run on a phone, or you want to run efficiently in the cloud, be it like neural network translation, image to image models, computer vision models like semantic computation, like for all of these, it's very, very, very important to run them efficiently. I think there's like a general tendency in the research on compression quantization that they're focusing on computer vision architectures. And there's some literature on like RNNs and transformers, but it's not a very large amount. But in general, we're interested in all of them.
What's driving that? Is that because they're starting out very inefficient or big or power hungry, or is it just that's what we're using more of?
I think it's also what we're using a lot of, right? Like if you look at deep learning algorithms on the phone, yes, there's some like neural machine translation models, etc. But the large bulk of that is still happening in the cloud. But a lot of camera algorithms are already on phones nowadays. Mm-hmm. So I think most of the efficiency work because of that is in the computer vision area. And also if you look at conferences, right, like the biggest conferences are computer vision conferences, and those people do a lot on these efficiency and compression kind of algorithms. So I think it's just because of the necessity of the market. But slowly but steadily, once more algorithms make their way to efficient devices, I think we'll see like a lot more work on like sequence models and other types of models.
And so the impression that I'm getting from hearing you describe compression is that, I may start with kind of an off-the-shelf model for computer vision, like a VGG, and then kind of train it to, solve whatever problem I'm trying to solve, and then put it through this compression process, as opposed to starting with a compressed network and train it. Is that correct? Or is the way that we're trying to get to smaller computer vision networks, starting by training big networks and then compressing them? And, as an alternative to that, is there a path to like just starting with a smaller network architecture and training it? And if not, why doesn't that work? What are the issues associated with the way we approach this problem?
Yeah, I think that's a great question and very fundamental to the kind of work we're doing and deep learning in general, perhaps. So basically, if you want to like make a efficient network architecture, I would always start with just making your network smaller or something like that, right? You don't want to have a network that's like 20 times too big and then say, okay, now we're going to compress it. I would rather say, well, if that's the case, just tweak your architecture in some kind of way and get a more efficient architecture and use that. But then afterwards, like if you have this efficient architecture, like a mobile net, for example, or an efficient net, it still helps a lot to compress it afterwards. And there's this theory, like this theoretical paper called the lottery ticket hypothesis that was recently published. And this kind of posits and also proves to a certain extent that you're better off like training a large neural network, something that's like over parameterized. There's a lot of filters and a lot of parameters, and training that first, and then making it smaller afterwards. And that's generally better than training that smaller resulting architecture from scratch. So I think the current consensus is that it's better to do that. Just start with the big model and then make it smaller.
And why is that? What does that paper at least suggest is the reasoning for that?
The paper suggests that basically you want to find like a lottery ticket. So the lottery ticket is basically a network architecture that's very good for your problem. And every feature will have like a certain probability of being a good feature to use. So what the neural network is doing during training is that you want to find features that are initialized close to good features, and those will be used. And then during training, the rest will be like pruned away or like removed or set to 0 because of your regularization. And now the more parameters you have, the more feature maps you have, the higher the probability you have of finding those optimal features that you can find. So because of that, you're better off training with a large network that is very over-parameterized. So you have more shots at finding the correct architecture, and then removing or regularizing away the smaller ones.
So each of your parameters is buying a lottery ticket, and a network that works well for your problem is a winning lottery ticket. And so they're theorizing that it's better to start with a winning lottery ticket and find a way to make it better than it is to start with a smaller network, fewer shots at finding that winning lottery ticket.
Yeah, exactly. It's like as if you were looking at, for example, you have a hole in a big table, and you can randomly distribute balls over this table. And if you want one ball in the table, and you want to minimize the distance that it takes you to roll the ball from one part of the table to the hole, then you're better off having 50 balls on the table and then pick the smallest, the closest ball and putting that in the hole. Then you might have to move a few centimeters, rather than picking one ball and putting it randomly on the table, and then you have like a very large distance. So you're trying to minimize the distance between your optimal features and what you initialize.
And so the lottery ticket hypothesis kind of flies in the face of your previous advice, which is to not start with something that's massive and start with something that's smaller. How do you rationalize those two perspectives?
Yeah, so I think it's a part of scale. Like I think if you start with a network that's like 20 times too big for what you eventually want, then you get to this point where it's actually pretty difficult to create algorithms that compress these networks efficiently. At least in my experience, the current tools that we have to compress networks are not very well equipped to prune a network by such significant amounts. Because you have to imagine that removing parts of the network and then training it while removing parts is also a very difficult task for the network to do. There's a lot of discrete optimization going on there. It's very difficult to train networks and prune them at the same time. So those numbers are too big. But definitely if your network is 2 times or 3 times too big for the original size, then just train it on the larger size and then prune it down and make it smaller.
And so how do you know if the network is 2 or 3 times too big or 20 times too big?
I think that's trial and error. So, I mean, one of the most basic things that you can do is just take your network that you've already designed and see what happens if you remove the amount of channels by a factor half. Like you reduce everything by 50%. Then reduce it to 25% or 12.5%, etc. And that can kind of already give you a pretty good idea of how over-parameterized your network is.
Yeah, it's funny. I talk to a lot of people, particularly folks that are on the applied side of things. So they're not in research. They're not trying to develop new network architectures. And 90% of the time, what they're doing is they're picking up some standard network architecture off the shelf, training it, and it kind of works. And they're like, thumbs up, hey, we've got something that works here.
Yeah, let's go. Let's put it in a product.
let's put it in a product, right? And so, granted, most of the time they're not working on putting it in a phone, but let's say that that they are. They've developed something that can look at a let's say a medical image and identify some kind of feature in that medical image, fairly successfully on a computer, and they want to get that onto a phone. And they've, trained it using, something off the shelf, like a VGG or a ResNet. What are the specific steps that, they would take, to get from there to, a model that is, more efficient running on that phone? Do they toss that out and start from scratch on something smaller and then optimize that, or do they kind of play with it in certain kind of ways? Walk us through the way that you should approach this.
I think generally those types of architectures are already quite well. I mean, apart from VGG, of course, but the ResNet architectures are generally already quite efficient for the tasks that they're designed for. The classification or semantic segmentation or object detection. For those, I would just start with compression. Just take your model that you've created, and then there's multiple algorithms that you can apply. Things like tensor factorization algorithms that decompose like one layer into multiple layers, or channel pruning type of architectures where you're actually removing complete channels from your network. And there's some libraries out there, right? And a lot of papers on these topics that you can look into. So apply these two types of algorithms, and you can make your model like 2 or 3 times smaller than original. That's generally what we see for most applications.
And so you've mentioned a couple of these algorithms: tensor factorization, channel pruning. Are there other major ones?
I think those are like the large categories. I mean, it kind of really depends on what you're compressing your network for, right? Are you compressing it for latency? Are you compressing it for power consumption reduction? Or you just want a smaller model to transfer to some other device? But generally, if you're looking at things like latency or power consumption reduction, then yeah, those are the major ones for compression. And afterwards, the quantization step is arguably even more impactful, and then even bigger numbers in terms of efficiency.
Before we get to quantization, let's stick with compression here. So you're compressing for latency or power, and you've got these couple of methods: tensor factorization and channel pruning. Are these kind of blunt tools that you're just kind of throwing at your model? Like you go to GitHub or something and download a tensor factorization script and you just run it and, it spits something out? Or is this a process that you're kind of exercising with some degree of care?
Yeah, so one of the interesting things that we're working on is to make all of these kind of algorithms work very easily out of the box, so that you can just apply it to any type of algorithm, right? Any type of deep learning network, and then without any effort actually doing this. But this is still not completely solved yet. There's not really a lot of good libraries that you can just download and use, and then without any hassle compressing your network. Generally, it's still a process of applying these techniques, either factorizing your weight matrix or removing some channels with some smart algorithm, and then doing a lot of fine tuning and a lot of handcraft tuning on top of it. So I wish it was as easy as just downloading a library and applying it. But generally, it still takes like a week or a few weeks to get this done properly.
Okay. So you need to understand a little bit about these different techniques in order to actually apply them at this point. So maybe walk us through tensor factorization. When you're starting this process, what is it that you're actually doing? How do you need to think about the process?
Yeah, sure. So the tensor factorization is basically the idea of decomposing your weight tensor into something smaller. And then in the end, what you end up with is instead of having one layer where you just do one convolution, for example, or in the case of RNNs, one matrix multiplication, is that you do 2 smaller convolutions or 2 smaller matrix multiplications. That's the general gist of it. So what do? Well, you take a network, then you have to somehow decide for each of the layers in your network how much you want to prune them. So how much do you want to reduce them in size? There's some smart algorithms for choosing this setting. And after you've done that for each of the layers, you compress it, basically by applying SVD on it. So SVD is like a very standard algorithm of doing tensor factorization. especially for convolutional neural networks.
SVD meaning singular value decomposition?
Exactly, that's it, yeah.
Okay.
So you basically apply singular value decomposition on it, get two smaller submatrices with a lower rank, and then you have two layers instead of one. And after you've done that for the whole network, you fine-tune it for multiple epochs to get back to the original accuracy. That's generally how that's done.
Okay. And you mentioned there are some algorithms to tell you which of the layers in your network you want to apply this to. What are those algorithms, and what's the general kind of intuition behind where you want to apply this?
Yeah, so I mean, there's a couple of them. I think one of the most recent ones that's interesting is called automatic model compression, or ANC, which is from Song Han's group at MIT. And this algorithm basically applies a reinforcement learning algorithm on top of the network. So it tells you, based on reinforcement learning, every iteration gives you a value, namely what is the accuracy of your network after compression. And the reinforcement learning agent optimizes the pruning ratios for each layer. So how much am I compressing each layer, such that your accuracy stays very high. So that's like one way to do it, for example.
And is it deep reinforcement learning, or is it more traditional RL?
It's like an actor-critic model. It's not very deep.
Okay, got it. Okay.
Yeah, pretty standard, but still recent. Yeah.
Okay.
Yeah, that's one way of doing that. Yeah.
Are there others that are worth knowing about?
Yeah, so one of the things that works very well is just looking at the singular values of your layers. If you're doing tensor factorization, for example, that also works very well. So basically looking at the residual energy. Yeah, so I don't know how technical or in depth I should go here, but
no, let's do it. So let's go deeper.
Well, just look at the singular values. I think that's as deep as we perhaps should be going. So the singular values are like a rough indication of the residual after doing the tensor factorization. So you're basically looking at the Frobenius norm of your weight matrix, or even better, of your activation set of activations. So generally, you feed some data to your network. You look at the output tensor for that, and then you decompose that. And so you can look at the residual energy, so that the singular values give you an indication of that.
But now we're applying this to determine which of the layers of our network we want to apply SVD to. I thought it sounds circular here.
No, it's not really which layer. So every layer you probably want to decompose, since almost all layers you'll find have some redundancy in them, but some more than others.
Okay.
So sometimes you have a neural network layer that is very redundant. It almost didn't learn any useful features. Sometimes you can even completely cut out layers out of the network, right? Especially residual networks, that happens sometimes if they're very deep. So it's really what you want to do is try to figure out what the prune ratio is for each of the layers. So for each layer, how much should I reduce it?
Got it. And so you're applying this layer by layer, but in order to determine these prune ratios, you need to be looking across different layers to try to get at what the redundancy is of a given layer, as opposed to within layers independent of the other layers. Is that right?
So yeah, sort of. Yeah. So it's kind of sometimes you can look at the layers independently, but it's definitely better to look somehow at the data distributions of each of the layers. And you're most better off starting at the start of the network, putting that one first, seeing what effect it has on the whole network, and then doing that iteratively from the start to the end of the network.
Yeah. Okay. Got it.
Exactly. Yeah.
Okay. So that's tensor factorization, and then there's channel pruning.
Yeah, that's channel pruning is basically the same idea. So, but except for you don't do any factorization, but you just say, hey, which channels from a network can I safely remove? So, I mean, every network is going to have some redundant channels. If you look at a standard ResNext architecture from PyTorch, for example, you'll find that some of the layers in there, you can remove half of the features and not decrease your performance at all. So networks generally have a lot of channels that are useless.
And so when we're talking about channels, we're talking about the width of the network, essentially, at the different layers.
Yeah, exactly. Yeah, so the input and output channels, right? So each residual block, for example, has like 64 or 128 channels, and then a lot of those can be removed without losing any accuracy in your network.
And so what are the kind of practices for determining which of those can be removed? Is it kind of a most significant, least significant ordering, and you can just kind of draw a line somewhere and see how the network performs, or do you have to look at it on a channel by channel basis to see what the importance of a given channel is?
Yeah, there's a few different indications. You can look at the weight magnitude of each of the, let's say you want to prune an input channel and you want to prune, let's say, 10 out of 128. You can just find the ones that the in terms of magnitude, the weights of the input channels, the lowest value, and you prune those. Those are generally the ones that are less important. Mm-hmm. There's some ways of calculating the sensitivity of each of the input channels based on the Hessian. Or like a recent paper called Eigendamage does this based on like a Kronecker factorization.
Eigendamage?
Eigendamage, yeah.
Oh, that's a great paper name.
yeah, it's an ICML paper from this year.
Okay.
It's a really cool paper. It's definitely recommended to read. So this looks at the sensitivity function. So basically, you calculate the Hessian of the loss function, and then says, okay, which ones are more important and which ones are less important, right? And then the least important ones you throw away.
And so you're throwing away these various channels. You made a comment about if you want to throw away 10 out of your 128, are you generally starting with some idea of the number of channels you want to throw away and then kind of testing so starting with an idea of the number, then determining of the, which do you throw away to get to that number, and then testing performance, and then just kind of iterating, that loop to determine what the best number is or how many you can get away with throwing away?
Yeah, basically like that. Or you could take this AMC approach, for example, to automatically, with reinforcement learning, figure out what the prune ratios are of the layer. You can make it dependent on the sensitivity metric that I just mentioned. There's some different ways. So generally, how you do it is you say, let's test this out. I want to compress my model by a factor 2, right? And then the algorithm automatically finds in some way how to set the prune ratios for each of the layers, such that I get to a latency reduction of, say, a factor 2. Mm-hmm. And then you take that. And then you remove those channels, make the model smaller, and it's going to be 2 times smaller.
Yeah. And so you mentioned that we're not quite at the point where, we've got kind of auto compression for these networks. And yet it sounds like a very kind of iterative process that we could, apply automatically to networks. What's really in the way of doing that?
Yeah, that's a great question. I think just the literature in compression is just very, very recent and very new. We yet have to figure out like a proper relationship between, for example, what type of error do we introduce in the network when we compress a layer? And if we look at that error, how does it propagate over the rest of the network, right? How does it lead to a loss at the end of the network? Because generally, for example, you can compress a layer and exactly figure out how to compress the layer and minimize the residual error that you get when doing so. But sometimes errors are very, very impactful at the end of the network, right? And sometimes errors are not. And trying to figure these things out, I don't think that has been sensibly done yet to really solve this issue of how to do this automatically.
And so maybe asking it a different way, if, let's say compute wasn't an issue, and obviously it always is, and that's a big part of the challenge. But let's imagine a world where compute was free. It sounds like what we're doing here is just kind of, a big loop of loops kind of thing. Then it could be done iteratively and you could brute force it. And so do we have any kind of intuition for, if we started with some kind of reasonable defaults or something for a given class of network, like what the ratio between the brute force compute that we would use versus the compute we would use if we took a more reasoned approach?
Yeah. A completely brute force would just be prune every channel, fine tune for a complete epoch for every pruning that you do. What scale do you want it? I think I can create an algorithm for you that's going to take 100 million years to do this, or cost you €1 million. But
hey, if I can have this thing running for 100 million years and it only costs me €1 million, that sounds like a pretty good deal.
We're going to do it on a very efficient Qualcomm chip. No, but yeah, I have no idea about this question. Sorry.
Yeah. Okay.
No good intuition here.
Yeah, no, I guess, I'm trying to get at like where the intuition is in this process that we just don't know how to encode versus, what is just kind of researchers and data scientists applying, rotely that the computer could do itself. And I don't feel like I fully captured like what the intuitive process is here that, requires us to manually do this.
Yeah, I also don't know yet, to be 100% honest. So I think parts of this can definitely be automated. And there, like I said, for example, this AMC, this automatic reinforcement learning based algorithm, is partially automating it, right?
Right.
Albeit with a reinforcement learning algorithm that's just trying a lot of things in a smart way, rather than us having a proper understanding of what it means for a layer to add a certain amount of information to your representation, for example, or how much expressive power does a neural network layer or like a group of layers need to have to really do the job it needs to do, right? These are all very, very unexplored questions in deep learning at the moment, I feel.
Yeah. Well, I feel like deep learning there, even before we get to compression, deep learning has a lot of unexplored issues, and we're managing to figure it out and automate a lot of it. Anyway, so that's kind of the compression side of things, and we let's walk through quantization in the same way. So quantization is what you gave us a summary earlier, essentially trying to reduce the number of bits we're using in each of these channels, right? As opposed to removing channels, now we're removing bits per channel. Is that a fair way to look at it?
Yeah, in essence, you're reducing the amount of bits of your weights in the network, and you're doing it for the calculations. So instead of doing calculations in floating point 32, you could do your calculations in int8, right? And then you're 4 times more energy efficient when it comes to memory transfer, and you're going to be 16 times more efficient when it comes to doing the actual calculations itself. So just by going from floating point 32, where you're doing all the calculations, if you have some kind of MAC array that's 8-bit, like unsigned or signed or whatever, then they're going to be a lot more efficient. This is one of the most impactful things that you can do to make your network run more efficiently on devices.
And
the easiest.
Okay, yeah. And now my sense of where things are with regard to quantization is that a few years ago when I talked to folks, I think my interview with Shubho Sengupta, very early one, he was talking about his experiences at Baidu building their neural machine translation system. And they were experimenting with quantization, and it was a very manual process, right? They had to, spend a lot of time figuring out where in their networks they wanted to apply quantization, how to do it without introducing too much noise, all that kind of thing. My impression is that, over the span of a couple of years, we've come a long way from that. And in a lot of cases, the infrastructure and the libraries, on top of that infrastructure, TensorFlow, for example, gives us some of that stuff for free. Like we can flip a bit and like quantize our network, and achieve reasonable performance. Is that the case? And if so, in a qualified way, like what's the envelope around that, that qualification? When does that work? When doesn't it work?
Yeah, so that's actually a very, very interesting question. Something that we've been really deeply looking into. Yes, some networks can be very easily quantized. If you pick almost all of the ImageNet trained networks, even the ones that are like object detection or semantic segmentation on top of the base network, many of those can just be 8-bit quantized with your standard TensorFlow tools. Sometimes you have to fine tune a little bit with the operations in place and train a network. But generally, those are okay. And then some networks seem to have a lot of issues. You can look at mobile nets, for example. So most of the mobile nets out there, like the mobile net v2, even the v3 version, if you just naively quantize it with the TensorFlow operations, everything breaks. You get like 0% accuracy. And sometimes, so we've also looked at things like image-to-image networks, right? So, networks that do, for example, things like style transfer or super resolution or these types of networks.
Yeah.
And then sometimes in these networks you can just 8-bit quantize, no problem at all. Works out of the box. And some networks don't at all, and it's very difficult to put our finger on why exactly that is.
And so do we have any kind of intuition at all, or are we still, we recognize that there's this distinction between the different types of networks, but really have no idea what or why it's happening?
Yeah, so in our recent paper called DataFree Quantization, we've investigated a lot of these issues and why some networks are very difficult to quantize. One of the biggest issues generally has to do with the ranges that you set. So you have to create some kind of quantization grid where you say, okay, these are the values I'm going to represent with the 8 bits that I have, let's say. Now for this grid, you have to choose like a minimum and a maximum, right? And generally everything, all of the points in between are like equidistantly spaced, and those are the values that you can represent, both for your weights and your activations. Now how you choose that range, the minimum and the maximum, is incredibly important. For example, you could have some outlier weights, and those weights then determine what your min and your max could be. If you just set your min and max of the quantization range to the exact min and max of your weight tensor, there could be one big outlier somewhere, and that could ruin the representative power for the rest of your weights. So a lot of you can only have a few points that are representable in the weights that are small, and then the big one is taking a lot of the bandwidth. So a lot of issues in quantization come from that, the fact that you set your ranges improperly. And the second one is that while you're quantizing, is that you can sometimes quantize in a not so smart way. For example, you could have a bias in your quantization, especially in MobileNet. If you have like a 3x3 filter that maps an input to the output, if by accident you quantize all the values of your 3x3 filter down, then your average output of that channel is going to be lower, and you're going to incur a lot more loss than if everything was like randomly flipped. So those are like two major issues when it comes to quantization.
Does the DataFree Quantization paper that you referenced, does it propose an approach for addressing these issues?
Yeah, definitely. Yeah, so there's multiple things in there that we've looked into. Basically, the DataFree Quantization paper was born out of this idea that many methods that help with quantization require a lot of effort, right? So generally how this works is that somebody tells you, okay, change this neural network architecture to this architecture, and then it's easier to quantize. Or do a lot of fine-tuning on top of your architecture and a lot of training with a lot of hyperparameters, etc. Now, if you want to make sure that like 8-bit networks can be run everywhere, it's very important that this is as hassle-free as possible, right? If I'm a cloud provider and I want to run my customers' models in 8-bit, I don't want to require of them that they got their PhDs in quantization just so that they can make more efficient models. You just want to make something that's basically you snap your finger and then half your network is gone, right? And it's like 2 times smaller. Mm-hmm. So that's kind of the idea of the paper. And then we said like, okay, what can we do to make that even further, right? Can we do this without using any data at all? So many methods use data to set the ranges, etc. And then the idea of our paper is like, okay, what can we do to make sure that this is as easy as possible? Like customers don't even have to give data to the algorithm to quantize it.
And when you say give data to it, meaning the quantization happens as part of a training loop or process, or is there some other process that is being applied?
Yeah, it's very often that, right? You take like 100 batches, you run them through the network, you get some idea of the activation ranges, right? That you get. The activation ranges help you inform what your min or max setting is for the tensor that you're quantizing. It's basically that idea. Yeah, so give a couple of 100 batches to the algorithm to figure out those ranges, or to even fine tune a little bit, right?
And so this paper proposes a way to allow you to skip that, avoid an approach that requires that you do this with regard to data.
Exactly. Yeah. And so the complete DataFree part is more of like a mental exercise. It's very interesting for like a paper, and we were able to get really good results, like state-of-the-art results on compressing things like MobileNet or some object detection networks with even that hard restraint in place. Now, in practice, you can often just use a couple of batches and improve your quantization performance. But basically, the algorithms we put in the paper can be used for either case. The most important part is that you don't have to do any fine tuning. So this is the difference between like getting your network quantized within an hour, or having to spend like a couple of weeks with like an expert in the field to make sure that your algorithm is quantized properly.
Mm-hmm. And so how do the algorithms work? Is it multiple algorithms, or is there one algorithm?
Yeah, there's a couple that we kind of stitched together to form like a complete quantization pipeline. So for this paper, one of the things we do is equalization. So remember these ranges that I talked to you about, right? That sometimes these outliers can cause some of the issues.
Right.
Now for our networks that are ReLU or Prelude based, what you can do, you can actually move scaling factors around in the network. So for layer one, if you look at the output, you can multiply that with a certain scaling factor, and then for the next layer, which takes as input the output of that previous layer, you can multiply it with 1 divided by that scaling factor, and you get mathematically exactly the same network. And by moving these scaling factors around, we can make the general min-max ranges. So these big ranges, we can make them smaller, such that the network is easier to quantize.
And so these min-max ranges, are you applying them on a tensor by tensor basis, or is it across the entire network?
Yeah, so there's multiple ways of doing this. So depending on the hardware that you're looking at, you can do it in different ways. But generally, there's two major categories that you do for quantization. One is that you do it per tensor. So each layer has its own set of min-max ranges. So that in turn translates to its own set of offset vectors when you do all the calculations. But setting that aside, you can do it per tensor, or something that was more recently introduced by a guy called Raghu Krishnamurthy. And he introduced, so he's from Google, he introduced per channel quantization. So that each individual channel has its own min-max range. And that solves some of the issues.
Okay. But presumably requiring a more complex training process because you have a lot more of these offsets to keep track of?
I think the larger drawback of it is that not all hardware supports it. So you have to make sure that your hardware supports, and the kernels for that as well, support the calculation of like per channel min-max ranges. Not all hardware does that.
Okay. And why is that dependent on hardware as opposed to the training process or something else that can be taken care of in software?
I mean, if you run things on like a CPU, of course, yeah, you can simulate everything on the CPU and it'll run efficiently. But if you have like dedicated hardware for inference,
got it. So if you're doing low-level operations and pushing everything down to those low-level, hardware modules for speed, then you're kind of stuck with what they're able to do.
Exactly. Yes.
Okay.
So yeah, that's one possibility. And another thing we do in the paper is we correct for this bias that I mentioned before. So sometimes because of rounding issues, you have to choose: am I either rounding up or am I rounding down each of the weight factors? You can kind of correct for some bias that you might introduce in doing that. And that's an algorithm we dubbed bias correction. And those two together really make most of the networks that we've tried, make them very easy to quantize.
Okay. And are there any kind of dependencies on the training approach you're taking in terms of things like whether you're applying dropout or like your learning rate? If you're doing cyclical learning rates or anything like that, or is this all independent of the way you train your network?
Yeah, I think it's completely independent. So this approach, this DataFree Quantization approach, in essence, you can just take any network. You can equalize it if there's like ReLU and Prelude units in it. And then the bias correction you can always apply. And that should give you better quantization performance. And we do it without any fine-tuning. So there's no hyperparameters. You just it's like a simple API call. You just throw your model to like an API call, it optimizes it for quantization, and bam, you get a quantized network.
It is hardware independent, or are there dependencies on the hardware with this method?
Nope, not at all. So it's all per tensor quantization that we do in the paper. So that's implemented in everywhere, in every hardware that I know of. So yeah, that optimizes it for any architecture.
And so what kind of results did you see relative to other ways that you might quantize?
Yeah, so one of the problems that you have, for example, with MobileNet v2 is that you actually get no performance after naive quantization with like TF Lite, for example.
Mm-hmm.
And we gained in our paper almost all of the performance. So usually you go from like 71.7% down to zero. We got to 71.2%. So that's only like 0.5% loss when going from float 32 to int 8. And that's, of course, like going from float 32 to int 8 is a tremendous gain in terms of power efficiency and in terms of latency.
And to what degree does that result generalize to other models, or is it just working for MobileNet v2 sufficiently applicable that you think it's important?
I think we've also in our paper seen gains in residual net architectures. We've seen it on multiple tasks like object detection, semantic segmentation. So really, because when you're doing equalization, your network stays mathematically equivalent, so there's definitely no loss, and it can only help for quantization. Similarly, for the bias correction, there's no negative drawbacks to this. So in most settings, it will help you. Rather than there's like no real probability that it's going to hurt you. So you can always test it. And I think in many of the cases we've seen this far, this really helps a lot.
Awesome. So, given this paper, which is relatively recently, and some of the other things that we've discussed, in terms of where the field is overall, what are you most excited about? Where do you see this all going?
The whole model efficiency point, you think? You mean?
Yeah. Just in terms of our ability to, take these models, which are getting bigger and bigger, and have them work on devices which we want to last longer and longer from a battery perspective, and have user experiences that are faster and faster.
Yeah, I think all of this stuff on model efficiency is like key for the adaptation of neural networks in many practical applications, right? I think on the cell phone, we're always bound by power and the amount of power that you can use. Mm-hmm. Nobody wants to have their battery drained within half an hour, right? We all expect our phones to last the whole day. And the same goes for like robotics but even for cloud, for big cloud players. If you could reduce the amount of energy that you're using by factor 2, that would be a tremendous decrease in the energy bill that you're paying. So I think a lot of our performance of algorithms is very restrained by, in practice, in practical settings, is constrained by how efficient our algorithms are. So the more efficient we can make our algorithms from a compression point of view and a quantization point of view, the higher the adaptation of these algorithms will be. We all know these numbers also about like how like training a network, for example, how training a network with like neural architecture search costs like the same CO2 output of like 10 jumbo jets flying back and forth for like 10 tour trips or something like that.
Right.
If we can do quantized training, like training in 8 bits, we can reduce that power consumption by a factor 4. So I think all of these things are crucial for the adaptation of deep learning.
And are there specific directions that you're excited about, either in your research or in the research that other folks are doing, that you think are particularly promising in helping us get there?
Yeah, definitely. One of the important trends I've been seeing in the compression literature, so some things from Song Han's lab or Vivian Say's lab at MIT, is like coupling the hardware and the compression and quantization and model efficiency together. So that you can like design deep learning algorithms specifically for hardware. And then you get totally different results if you optimize your network for the CPU versus if you optimize them for your GPU versus if you optimize them for like a DSP in a Qualcomm device, for example. Mm-hmm. So if you're looking at a CPU algorithm, because all of the calculations are done sequentially, these architectures are usually very deep and have like 3x3 convolutions. But if you create an algorithm that's optimized for the GPU, you generally get larger layers, like 5x5, 7x7 convolutions, for example. Mm-hmm. So I think it's a really interesting trend where, given the hardware that you're going to run it on, can we optimize the algorithm to run efficiently on that? I think that's really cool.
Cool.
Yeah. So it's a better marriage between the hardware and the algorithms that we have.
And hopefully, ultimately, this gets us to a point where, as a model developer, I have to think less about these kinds of issues, and it all just kind of works for me.
Yeah, especially for quantization, I think that's very, very much in reach. So my vision is that literally every neural network architecture can be ran in 8-bit. I think that's very possible.
Mm-hmm.
And currently we're seeing that almost all algorithms are still being run in 16-bit, right? Yeah. So getting that to 8-bit would be like 2 times more power efficient in many cases, and then we can run a lot more AI on our phones.
Awesome. Well, Tijmen, thank you so much for taking the time to chat with us about what you're up to.
Yeah, thanks a lot for having me. It was great explaining all the compression and quantization stuff we've been working on.
Yeah, absolutely. Thank you. All right, everyone, that's our show for today. If you like what you've heard, please do us a favor and tell your friends about the show. And if you haven't already hit that subscribe button yourself, make sure you do so you don't miss any of the great episodes we've got in store for you. Thanks once again to Qualcomm for their sponsorship of today's episode. Check them out at twimlai.com/Qualcomm. As always, thanks so much for listening, and catch you next time.